Object-oriented programming is built on the promise of encapsulation. When you create a class in Java, you are defining a blueprint where every new object is supposed to manage its own private state and independent behavior. Take Rahul, for instance. He writes a Java backend to manage his household finances, initializing two distinct bank account objects, one for himself and one for his wife, Anjali. He deposits 5 lakh rupees directly into his own account instance, but when Anjali logs in and checks her distinct account, her balance also reads 5 lakhs. They assume the bank made a highly lucrative clerical error, believing their financial data is independently secured within their respective objects. Riding high on this unexpected windfall, Anjali immediately pays 1 lakh for the house rent, pulling the funds strictly from her own account object. Across town, Rahul's phone buzzes with an alert. His separate balance just dropped to 4 lakh rupees. The illusion of financial independence shatters. He panics, accuses Anjali of draining his personal funds, and a massive household argument breaks out. Rahul is looking at a massive financial discrepancy. Anjali performed a transaction on her specific account object, yet the data inside Rahul's supposedly isolated object changed simultaneously. We need to play debugger and dive straight into their backend Java code before this financial dispute leads to a class action divorce. Scanning the bank account class, everything looks normal at first glance. Standard variables like account holder name and account number are properly declared. Then we find the code that broke the household. Static double bank balance equals 500,000. The static keyword tells the Java virtual machine this variable belongs strictly to the class blueprint itself, bypassing individual object instances. Rahul thought he was coding 2 separate accounts, but he unknowingly created a single shared variable wearing 2 different masks. To see how this broke down, let's look at the architectural map of Java's memory. Here on the left is the heap, where normal instance variables are allocated into separate, isolated boxes. But the word static evicts a variable from the heap. Over on the right is the metaspace. The bank balance lands here, in a single, globally shared zone. In domestic terms, this is a total breakdown of boundaries. It's the software equivalent of declaring a static family toothbrush. You only have one, and everyone is forced to use it. By sharing memory space at the structural level, every spawned instance is permanently entangled. Sharing memory guarantees sharing problems. With their relationship hanging by a thread, Rahul and Anjali sit down at the laptop to refactor their architecture before they go entirely broke. The fix is remarkably simple. We delete the word static from the balance variable. By removing that keyword, the data is bound back to the local instance scope. Down on the heap, the single balance instantly splits into 2 independent memory blocks. Out of scope, completely out of mind. Correctly aligning the variable scope with their real-world logic restores encapsulation, granting them total financial independence. All of this leaves a lingering question. If static triggers this kind of chaos, why did the creators of Java include it in the language? Static is actually built for shared architectural truths. Take utility constants that never change. If a bank has one IFSC code, you write it as static final double bank IFSC. Notice how hundreds of object instances draw a line to one single efficient memory block in the metaspace, saving the system from wasting space on duplicate data. It's also used for global trackers. If the bank needs to count every new user across the entire system, a static int total accounts opened sits in the metaspace, incrementing globally every time a new object appears on the heap. In Java, knowing exactly where your data lives is just as critical as knowing what your data is. The static keyword creates a crisis when it merges personal data, but it provides a highly efficient way to manage shared global state when applied correctly.